Hello, everyone. Thank you for joining this seminar series organized by the Empathic Computing Laboratory. I'm your host, Aladdin, and our guest speaker for today is Katharina Krösl, who is a senior researcher at VR-Vis in Vienna. Her research interests include mixed reality, perception, and medical simulation, and has done a lot of research since 2016 and won many awards for her excellent PhD work. The title of the talk today is Simulating Vision Impairments in XR, and the talk will be roughly an hour, followed by a brief question and answer session. Thank you for joining us, Katharina.
Thank you. Thank you for the nice introduction. Let me share my screen. Okay, so thank you everyone for coming to my talk today. I'm going to tell you about my work on simulating vision impairments in extended reality, or short XR. And this is actually research I started during my PhD, which I defended at the end of 2020. And I have a background in computer graphics and rendering. And usually in this field, the goal is most of the time to make images better, or prettier, or more photorealistic. So you might wonder why someone would do quite the opposite, degrade the visual quality of an image and simulate an impairment. And in this talk, I'm going to tell you why, how, and for whom we want to do these vision impairment simulations. Let's jump right into it. This is an image of a typical escape route sign. Everyone has seen these signs. They show the shortest path out of a building in case of an emergency. And such signs have to be installed at a certain maximum distance to the next sign, and also at a certain height. And so the goal is that people have always one sign in sight that they can see. But what if you have some form of visual impairment that makes it harder or almost impossible to recognize the direction on the sign? So this is actually a common problem for a lot of people. According to the World Health Organization, vision impairments affect about, or at least 2.2 billion people worldwide. And this number is expected to increase due to different factors such as aging of the population. And this is also because many eye conditions actually show a higher prevalence with age. And there have been many efforts to develop technology that can assist people with vision impairments in their everyday lives. Some researchers used Google Glass devices for that purpose. Here's an example from Huang and Peli, where they basically tried to create vision enhancements, like edge enhancements in augmented reality. Or some researchers used augmented magnification displays, like here in this example, using smartphones. Others also use HoloLens in combination with handheld smartphone, like you can see here in this example, with either with a smartphone or a finger-wand camera, which basically records what you what you have in front of you, like this book, and then you see a magnified version of this in your HoloLens, in a virtual desktop, so to say. Others also worked with video see-through AR devices and created applications that provide visual cues as aid for the user. And some even developed their own AR devices to compensate for vision impairments. Like this example, it's called chroma glasses and was presented by Langlotz and colleagues, and basically tries to enhance the vision of a person with color vision deficiency in a way that they have an easier way to distinguish colors that they, with their deficiency, have a problem of telling apart. While this is an important research topic, assistive technology alone will not solve every problem for people with vision impairments. These devices are expensive and many of them are still limited in functionality. And in order to make our society more accessible for everyone, we also need accessible design when it comes to cities, buildings, lighting systems, or signage. And we need to increase awareness for people with vision impairments. And in order to do that, we need to first understand the impact of vision impairments on perception. We could, of course, run a user study to investigate it. But in order to be able to quantify and statistically evaluate the effects of certain vision impairments on perception, we would need to get a really large number of participants, and they would have to have the exact same form of vision impairment, so the same symptoms and the same severity. And the problem is that the severity of symptoms is often hard to assess precisely. And even if you have two people with the same symptom and same severity, they might still experience it differently. So finding this user group is really difficult. And as a solution to this problem could be to run user studies with people with healthy eyesight and just simulate vision impairments. Some researchers already followed this approach and used physical goggles with special lenses or foils to create the effects of different eye diseases. And real goggles might be suitable for educational purposes, but they limit the experiment environment of user studies to the real world, where environmental changes like fire or smoke are hard to simulate safely. And each set of goggles only simulates one particular vision impairment. So you cannot adjust the severity of symptoms other than using a different pair of goggles or swapping the lenses. So this is not really adjustable to the vision capabilities of users. And a person who is a little short-sighted will have a slightly different experience than a person with normal sight when they use these goggles. Which again means if we want to run a user study, we have a problem because we then get people that have different impressions, different visual impressions. An approach that is used a lot to show people the effects of vision impairments is to modify 2D images. This has been used in various works on simulating color vision deficiencies, and also in web design in order to let designers test their websites for accessibility. The images you can see here are well-known images of vision impairments provided by the National Eye Institute of North America, and they inform a lot of research in this area. The obvious disadvantage of 2D images are that they are not immersive. They are still images. So they are not adjustable for individual users, and they also can simulate gaze-dependent effects. But many vision impairments are like the one you can see here in this image, like the diabetic retinopathy. They affect parts of your visual field. And so these effects move with the gaze of a user. And if we want to have a realistic simulation of vision impairments, we also need to move these effects with the gaze of the user in our simulation. So clearly we need something better than 2D images, something closer to reality and something more immersive. There's a whole body of research on simulating vision impairments in VR or AR with different limitations. Many simulations are simplified depictions of eye diseases and do not combine multiple symptoms to simulate complex eye disease patterns. You know, I've seen a lot of simulations that claim to simulate this or that eye disease, and they then just blur the image and that's it. And only very few simulations actually use eye tracking to simulate these gaze-dependent effects. And as I mentioned, this is crucial if you want to create a realistic simulation of a vision impairment that affects different areas of your visual field differently. And hardware limitations are another point that's rarely taken into account. And also vision capabilities of users. So if you use a different VR device, or if you have users with different eyesight, you have to account for this somehow if you want to create the same impression for everyone. And this is really important because the resolution of a display, for example, or the short-sightedness of a person could impact their perception in VR, and therefore create a different experience for them when they use the simulation. And I will get even more into this a bit later. So if we summarize the limitations of prior work, we can identify a few requirements for our vision impairment simulations. We have seen that hardware goggles or 2D images cannot provide an immersive simulation, of course. But this is vital if we want to understand how a person with a vision impairment really perceives or experiences the world. Eye diseases are a combination of different symptoms, and they can differ in severity. Therefore, it is important that we can adjust each symptom individually. And we need to combine multiple simulated symptoms to create simulations of complex eye disease patterns with gaze-dependent effects. If we want to use these simulations for user studies with healthy subjects, we need to make sure that our simulation is perceived similar with every user. Only then can we get meaningful results from statistical evaluations. So to sum this up, our final goal is to create realistic, medically informed simulations of eye diseases that can be used to raise awareness, train medical personnel, and help us understand the impacts of vision impairments on perception better, and also help architects and designers to test their designs for accessibility. To achieve this goal, we formulated some high-level research questions. Our first goal was to investigate how we can efficiently quantify the effects of a reduced visual acuity on the recognizability of signage. This is something that is important for the development of norms and standards that inform architectural design. And to answer this question, we developed a symptom calibration methodology that allows us to calibrate the simulated reduced visual acuity in VR to the same level for every user. And this then allows us to run user studies in VR with a lot of people with the same simulated visual acuity, which means it is suddenly easier to get enough participants with the same visual acuity to do a meaningful statistical analysis of the results. But we also want to enable architects and lighting designers to easily test their designs for accessibility for people with different vision impairments. This is why we developed an effects pipeline to simulate not just a single symptom like reduced visual acuity, but whole eye disease patterns such as cataracts, macular degeneration, or cornea disease, which are a combination of multiple different symptoms. So if we have this simulation of eye disease patterns, the question is, how do we know that these simulations are realistic? We looked at images in medical publications, and we also worked together with ophthalmologists to create medically informed simulations. But the only people who truly know how vision with a certain eye disease looks like are actually the ones who have it. So we wanted to find out how we can create realistic simulations of vision impairments based on the first-hand experience of affected people. And in order to do that, we developed a symptom matching methodology that allows us to adjust our simulation with together with the participants with impaired vision and match the impaired vision of an affected person. And this has to be done with people who have only one affected eye. So they can actually look at our simulation with their healthy eye, and then they can compare it to the impaired vision of their other eye. But we will get into this, into the details also a bit later. So let us start by looking at the symptom calibration methodology. In our user studies, we use this methodology to calibrate our simulation of reduced visual acuity to the same level for every user. But before I'm going to tell you exactly how we did this, I want to revisit a few fundamentals about visual acuity. Visual acuity describes a person's ability to recognize small details, and we can measure it with an eyesight test. And a common sign is used for eyesight tests that many of you might have seen somewhere already is the Landolt or Landolt ring, like you can see here. It is this ring which has a gap at one of 8 possible positions: left, right, top, bottom, or diagonally in between. So a common test distance for a visual acuity test are 6 meters or 20 feet. And a person with normal sight should actually be able to recognize a small detail like the gap in the Landolt of approximately 1.75 millimeters in size at 6 meters distance. And this corresponds to viewing angle of 1 arc minute. So if the smallest detail a person recognizes at 6 meters viewing distance is larger than that, larger than 1 arc minute, for example, 2 arc minutes, so twice the size, it means that the visual acuity of this person is half as good. So this person can recognize details that are double the size at the same distance, or half, or the same size at half the distance. Normal vision is also called 6/6 or 20/20 vision, or 1.0 in decimal acuity. So decimal acuity is calculated as the distance at which the test subject can recognize a small detail, divided by the distance at which a person with normal sight would be able to recognize the same small detail. So, for example, if my visual acuity is just half as good and I recognize a small detail of 1.75 millimeters only from 3 meters distance, it means that I have a visual acuity of 1.5 decimal acuity. So this means we can calculate which size of small details a person with a certain visual acuity should be able to recognize at a certain distance. And this is very important for our approach. The second fact that's important for us is that there is a relation of the sigma parameter of a Gaussian blur and the visual acuity of a person. And this was discovered by Hogerfrost and Van Damme. And we follow their findings and simulate a reduced visual acuity by applying a Gaussian blur to the image. So for our symptom calibration, we implemented a visual acuity test in VR, and you can see a screenshot of this here. We know which size of a Landolt-C a person with a certain visual acuity can or cannot recognize anymore. In a normal IC test, you would start with a large Landolt-C and then stepwise decrease the size to find out the visual acuity of the test subject. But we don't do that. We start with a size and distance that corresponds already to a certain visual acuity that as we have calculated it. And then we keep the size and distance fixed. But we apply a Gaussian blur to the image and stepwise increase this blur, as you can see here, until the user is not able to recognize the gap in the Landolt-C anymore. Because then we have calibrated the vision of this user to the predefined level of reduced visual acuity. But we have a problem here, because a multitude of factors affect our perception in VR and AR, such as discussed, the vision capabilities of users, but also the resolution of the VR display. Then the fixed focal distance of the display, which can create a vergence accommodation conflict, possible misplacement of a display, latency, refresh rate, and flicker of the display, or the dynamic range and color correctness of the display. So this list is not complete, but it contains the most relevant factors that influence perception when we try to simulate vision impairments and calibrate symptoms in VR. What this basically means for us is that as soon as you put on a VR headset, you will already experience a mild vision impairment. So we acknowledge all of these factors and just add our blur on top of this. This means, for example, if you have two people with normal sight, but one sees a little bit better than the other person, you will have to blur the image of this person a little bit more than for the other one to calibrate both of them to the same level of reduced visual acuity. And I should mention here that when we talk about normal sight, people understand 20/20 or 6/6 vision, 1.0 decimal acuity. But normal sight is actually not one visual acuity value. It's a range of visual acuity above 0.8 decimal acuity. And it can go up to 1.6 or even 2.0 decimal acuity. So even people with normal sight don't see the same. Some see a little bit better, some see a little bit worse. And this means that even for people with normal sight, we need a per person calibration. Otherwise, we cannot create the same visual impression for all of our users. So we can use the same methodology to also reduce contrast. Only this time, instead of stepwise blurring the image, we just stepwise reduce contrast. And therefore, we are able to simulate a similar amount of contrast loss for all users. And we follow the protocol of the Pelley-Robson contrast sensitivity test here, but we still use our Landolt-Cs instead of letters like on the Pelley-Robson chart. In order to test our calibration methodology for visual acuity, we conducted a user study. In this study, we investigated the maximum recognition distance of escape route signs. This is the maximum distance at which a person is able to recognize the direction the sign is pointing to. And we tested 3 different conditions: no blur, weak blur, and strong blur. Our weak blur corresponds to about 5 arc minutes, so 0.2 decimal acuity, and strong blur would be 8 arc minutes or 0.125 decimal acuity, which is already a quite severe vision impairment. We measured the maximum recognition distances by placing the user at the beginning of a 40-meter long virtual corridor. And this corridor had an escape route sign at the far end, and we then asked users to advance in the direction of the sign, and as soon as they could recognize its label, they could indicate the recognized direction by pressing on the corresponding direction of the touchpad on the Vive controller. And this is how we measured the maximum distance at which a person was able to recognize such a sign. And we took measurements for different conditions, so different sizes of the signs, as well as different viewing angles. Here you can see the evaluation of our results. On the y-axis, we have the maximum recognition distance in centimeters, meaning the distance at which a person was able to recognize a sign correctly. And on the x-axis, we have 15 and 30 centimeter high signs at different angles, at 0, 30, or 60 degrees. And the box plots show the distributions of our measured recognition distances. So the farther the size, the better the person could see or recognize the sign, because they could recognize it earlier. And there are norms and standards in place that specify at which height, which size, and in which distance an escape route sign has to be installed. And the blue line here shows what this European norm prescribes. So according to this norm, a 15 centimeter high sign should still be recognizable from a distance of 15 meters, which obviously was not the case in our study. So this norm does not consider viewing angles or visual acuity, so it does not facilitate accessible design. I also have an example of an ISO standard here that does consider viewing angles, but it just scales the maximum recognition distance by the calculated visual acuity. And as you can see, this underestimates the maximum recognition distance when compared to our measurements. And this is also not what we want, because this means you would actually put up a lot more escape route signs than necessary. And the same ISO standard suggests to just reduce the normal maximum recognition distance by 40% if the percentage of normal sighted people is unknown. And this is the pink dashed line. So to be able to compare this to our measurements, we need to be aware that the norms and standards state that the maximum recognition distance has to be valid for at least 85% of all people, not for 100%, just for 85. So we cannot just compare them to the mean or median values of our measurements. And the green line here represents the maximum recognition distance that is valid for 85% of our participants. So 85% could see it from this distance or farther away. And now you can see that the ISO standard for an unknown percentage of normal sighted people, the pink dashed line, already slightly overestimates the maximum recognition distance for a mild vision impairment here on the left. And it's even worse for a more severe vision impairment, like we have simulated with our strong blur here on the right. And this is a form of vision impairment that you could actually expect in home for the elderly. You could have a lot of people with such a form of vision impairment. And at the time we conducted this study, none of the current standards and norms accurately or sufficiently took vision impairments into account, which is why we concluded that more empirical data and research was needed to determine the exact influence of vision impairments on recognition distances in order to create more accurate regulations. And I believe that virtual reality simulations are a good way to do this. Now we have seen how our symptom calibration can be used to investigate accessibility aspects. This is a fundamental methodology for enabling these types of studies because it allows to conduct studies with normal sighted people, which are much easier to find than people with specific vision impairments. And to the best of our knowledge, this had not been done prior to our work. And we published this in the Visual Computer in 2018. So now we can simulate and calibrate symptoms such as reduced visual acuity or reduced contrast. And you could also use this methodology to calibrate other symptoms. But in order to understand the impact of not just a single symptom, but IDC's patterns on perception, we need to be able to simulate these whole IDC's patterns that consists of multiple symptoms. And this is why we developed an effects pipeline to combine different simulated symptoms and create simulations of complex IDC's patterns. And the World Health Organization identified cataracts as one of the leading causes for vision impairments. And therefore we picked cataracts as our first target and created a cataract simulation. So for the ones who are not too familiar with this eye disease, cataracts are opacities in the lens of the eye, which occlude parts of the visual field and can also lead to vision loss when left untreated. Depending on the characteristics and the region of the lens that is affected, cataracts are categorized as nuclear, cortical, or posterior subcapsular cataracts. Cataracts can cause symptoms such as cloudy or blurry vision, faded colors, tinted vision, trouble seeing at night, increased sensitivity to light, halos around lights, or double vision. So a lot of different symptoms. And we worked with ophthalmologists who are experts in the field. And we concentrated on the most common cataract symptoms, because different people, they experience different symptoms. But the ones that are here in black, these are the most common symptoms that most people with cataracts experience. And then we created an effects pipeline to simulate the cataracts involving these symptoms in virtual and augmented reality. And we used the Pupil Labs eye tracker add-on in the HTC Vive Pro for gaze-dependent effects. And we used the Vive Pro's front-facing cameras for video see-through augmented reality. So for our effects pipeline, we combine different effects to simulate cataract disease patterns. First, we reduce the visual acuity of the user using a Gaussian blur. And so here on the left, you can see a video see-through augmented reality view of our lab. And here you can see it with this reduced visual acuity with this Gaussian blur added on top. And next, we reduce the contrast. So we use a histogram compression of luminance values in the CIE LAB color space. And we do this because this color space is actually perceptually uniform. This means that the lightness value L in this color space represents the perceived luminance of a pixel. And therefore, the histogram compression results in a perceptual contrast reduction. Then we apply a color shift. And the tinted vision that people with cataract sometimes experience is caused by particles in the lens that absorb or reflect parts of the incoming light. So here you can see an image of an eye with cataracts, and the lens often appears bluish white. And this part of the incoming light does not fall onto the retina. So therefore, the resulting color shift can be simulated by multiplying the image color with the complementary color of these cataract particles. And since this is actually a physical and not a perceptual process, we do our calculations in the linear RGB color space and not in the perceptual color space this time. Finally, we simulate sensitivity to light. And this can be done by applying a bloom or glare effect around the light sources. Here you can see our simulation when looking at a 360-degree image. So on the left, it's just the original image, and on the right, this is our simulation for nuclear cataracts, which cause a uniform clouding of the lens in the human eye. Cortical cataracts additionally create dark shadows in the periphery of your vision. And to simulate these shadows, we add one stage to our effects pipeline. So we essentially use a shadow texture to darken the periphery and use eye tracking to move this effect with a user's gaze. And this here is just an illustration of an eye with these shadows. And usually shadows become more or less prominent depending on the pupil size. And as you can see in this animation, if I look at a bright sunny scene, my pupil becomes smaller and less of the clouded area of the lens can affect my vision. And if I look at something really bright, my pupil becomes very small and light does not pass through any of the clouded area on my lens anymore. So I will hardly notice any shadows in my field of view. And in order to simulate this behavior, we just scale our texture according to the brightness around the gaze point. And this gives us a simulation of cortical cataracts. We can also invert our shadow texture to create shadows in the center of the field of view, which is actually a common symptom of posterior subcapsular cataracts. Before doing simulations in AR and 360 images, we started with a VR simulation of cataract vision. And we conducted a user study and again measured maximum recognition distances with our simulations of nuclear, cortical, and posterior subcapsular cataracts. And you can see here this black ring is actually the border of the field of view that the person in the VR headset would actually see. Our results showed that maximum recognition distances with cataract vision are significantly lower than with clear vision, which was to be expected. But clear vision in this context means actually wearing a Vive Pro headset with no simulated impairments. But the low resolution of the headset still causes a reduction in visual acuity to approximately 0.5 decimal acuity according to our tests. So you're already vision impaired if you put on a VR headset, basically. We let users explore a virtual environment with all three types of cataracts and compare two different lighting systems. And they could switch back and forth between lighting systems, and then we asked them to compare them and compare them for each cataract type and tell us which lighting system they preferred. Our results showed that lighting systems with many light sources in the field of view of the user are perceived as especially uncomfortable. And this was a user study with people with normal or corrected sight wearing glasses or lenses. So these experiments demonstrate how this method could be used in general by architects or lighting designers to test their designs for accessibility already during the planning phase of a building and make better decisions, because they could just import their designs into such a software and basically walk through them with simulated impairment. And our symptom calibration and medical informed simulations of eye disease patterns in VR now allow us to conduct controlled studies with participants with normal sight, which is much easier than to get participants with the exact same form of vision impairment. And we are one of the very few people at the time who used eye tracking for gaze-dependent effects. But this is really crucial for a realistic simulation, because some symptoms, such as these dark shadows that we have seen before, that are created by cataracts, they affect only parts of the visual field, and they really depend on the gaze of the user. And with our effects pipeline, which is actually quite easy to extend to add different symptoms, we can simulate different eye diseases where the severity of each symptom can be adjusted individually and at runtime. And we published our effects pipeline and the results of our study in 2019. And in 2020, I think was our book chapter on this topic. And I also did a live demo at IEEE VR 2020, where we presented our demo XRI. And yeah, the conference was had suddenly switched to virtual, like 2 or 3 weeks before. So I planned to do my demo in person, but then I had to do it remotely from home, showing interactive adjustments of symptoms for different eye diseases. And this was quite a challenge and a complicated setup, where I had the Vive Pro basically mounted to the back of my chair, so I could move it when moving my chair, so you would actually see the movement in the image. And the simulations we presented during the demo were developed also in close cooperation with ophthalmologists. But still, it's extremely difficult to visualize an eye disease when you're just told how it looks like and you have never experienced it yourself. So we asked ourselves the question, how do we know the simulation is correct or realistic? Or how can we make it as realistic as possible? And the answer to this question is our symptom matching methodology. So the idea is to get a person with an eye disease on one eye and ideally normal sight on the other eye to try our simulation. And using the HTC Vive Pro's front-facing cameras for video see-through AR, we can show the user the unmodified AR stream of their surrounding for the visually impaired eye and let them look at our simulation of their eye disease with their healthy eye. And this way they compare their eye disease to our simulation and help us adjust it at runtime and also evaluate it. So to test this methodology, we conducted a pilot study with 3 cataract patients between surgeries of their left and right eye. Between surgeries, because cataracts are usually treated by replacing the affected lens with an artificial one. And since patients often get surgery on their second eye a few days or weeks after their first operation, there is actually a very limited time frame in which they are uniquely qualified to evaluate our simulation by looking at a simulated cataract with their corrected eye and comparing it to their vision with their still cataract afflicted eye when viewing the unmodified AR video stream. In order to compare a simulation to their own cataract vision, we let them switch between the view of left and right eye, because this is much easier than trying to close one eye. I don't know if any of you ever tried this in a VR headset, but the headset won't be perfectly still and in place, so it's kind of tricky. This is why we just gave them the option to just switch the view from left to right. And we asked them to point out the differences and advise us also on how to adjust the simulation, which we would then actually do at runtime during the experiment, so we could match their cataract vision as closely as possible. And after we adjusted the simulations as best as we could, we also asked participants to rate the simulated symptoms and the overall simulation when compared to their own cataract vision. So our results from this preliminary study showed that the individually adjusted symptoms were deemed to be close to our participants' perception of the environment with cataract vision in a majority of cases. However, the overall impression of our simulation was rated worse than the individual symptoms by 2 out of 3 participants. So just always keep in mind, this was just a very short preliminary study with only 3 participants, but we got some insights from this. We of course, we have to run more experiments to look into this, but one explanation for this overall rating that was comparably bad could be that each individual symptom was close to what they perceive, but not perfect. So these little differences then add up in the overall impression. So the overall impression is then more different from what they are seeing. And we really wanted to include more participants in our study, but then there was a pandemic and we were not able to conduct further in-person experiments, unfortunately. We tried to add some more information to our study by conducting remote experiments. And we had 2 participants who had undergone cataract surgery a few months before. So we had a video call and streamed live images and communicated with participants via voice chat. And we asked them to compare the presented cataract simulations to their memory of their own cataract vision before the surgery. And we adjusted the simulation according to their feedback. We also showed them images from related work. And in this case, the adjustment was done by adjusting the opacity of the cataract image when blending it over the original. And both participants stated that overall our simulation best resembled their experienced cataract vision, especially for our night scene. But still, this is just the opinion of 2 participants. We have to run larger studies to get better results. So with this pilot study, we just tested the feasibility of our methodology, actually. But we also gathered some qualitative feedback. And with our remote experiments, we tested a way to compare our simulation to related work. So this symptom matching methodology enables us now to compare simulations of eye diseases to a ground truth, the impaired vision of affected people. And I strongly believe that this human in the loop approach can help us create more realistic simulations in the future. And we published our methodology and the findings from our first experiments at ISMAR in 2020. And this brings me to future work. As mentioned, we need to run larger studies with more participants in future work. We actually had an ethics approval for such a study, where we also planned to include medical data such as slit lamp images of eye lenses and compare findings from these data to our study results. But unfortunately, due to the pandemic, it was not possible for us to run studies because our participants are elderly people and we recruited them in a hospital. So these facts both made it unfortunately impossible for us to run additional studies with these participants. It would also be interesting to run studies with architects to find out how a solution like the one I presented you today could support them best, or in what ways we would need to extend our tool or adapt it to meet their needs so they can really evaluate their designs for accessibility. So this project has more or less ended with the publication of my dissertation in 2020. But we are looking for additional funding to start working on it again. And I would like to add more simulations of vision impairments and more calibration methods for different symptoms. And I'd also like to test it on better hardware, such as the Vario XR3, which from what I've heard has a very high resolution display that matches 20/20 vision, or so it's advertised. And I also want to investigate how we could extend our simulations to optical see-through AR. I mean, I think for many simulations, this might be really, really difficult, but for some vision impairment simulations that are more like occlusions in your visual field, this might actually work quite well and could be very interesting. So to conclude, I presented a methodology and system for conducting quantitative and qualitative user studies for visual impairments in VR, AR, or when viewing 360 images using eye tracking for gaze-dependent effects. And our methodology describes how to calibrate individual symptoms, combine them to simulate eye disease patterns, and adjust them with patients using our symptom matching approach. We tested our methodology in 3 user studies, and our experiments showed that current standards and norms at the time for signage should be revised to include people with vision impairments. And I'm happy to say some of them have, and I've been part of this. So we've been working on a new Austrian norm that better takes vision impairments into account. Our studies also showed the different lighting conditions influence the perception of cataract symptoms differently. So more passive lighting would be good in homes for the elderly, for example, or probably. And we also found that VR and AR systems can be used to create realistic vision impairment simulations together with doctors and patients. This is important. And they can help to increase the understanding for challenges people with vision impairments face every day. And here's the list of publications from what I presented today. And these are my co-authors that worked with me on these publications. And with that, I would like to thank you for your attention, and I'm happy to answer any questions.
Amazing. Thank you so much. It was impressive work, especially with what's happening with the limitation of COVID and not being very difficulty to find a patient to test the symptom matching with. And well
Indeed,
done.
indeed.
If anyone has question, please ask. It's only a few people of us. I would like to ask, I know that you said in the future work you would test it with architect and other designers of signage in the buildings. What would you expect they would do differently after experiencing this? Is that something you have like an idea what they may change in the design?
Well, as mentioned, you have these norms and standards that basically tell architects and designers how to mount escape route signs, for example. But in some cases, they are not sufficient, or maybe the design of the building is not ideal for a person with bad eyesight. And this is, I mean, for an architect or designer, this is really hard to know. If you can only look at what the norms say and use your best judgment. But if you have a means to experience it yourself with an impairment, you might spot some design flaws quite easily. Or you might see that, okay, a person with a low visual acuity cannot distinguish this sign from some decoration that's next to it, or might not be able to find the way out of the building. It's just an easier way to adapt your design or detect design flaws if you can see it with your own eyes.
Yeah.
So that's the idea.
Yeah, absolutely. And I'm just wondering, because some of these impairments, it's in the center of your gaze, and some of them also follow the gaze. And I was wondering how would, if we are designing something and accommodating to this, and I know once we observe it with our own eye, we would be able to think of alternative solutions, but I'm struggling now visualizing it myself. What would I change, I guess?
Well, I think especially when you think of impairments that affect your central vision, it's usually not that you don't see anything. You see something in also in the center of your vision, but you cannot really recognize it. So the important thing is that, for example, for these escape route signs, that you see that there is a sign, or also some visual guiding systems in general. You have to make sure that people recognize that there is a sign, and then they can just advance close to the sign until it's big enough so that they see the direction. But for example, if a sign is mounted very high above some stairs that go down, for example, it might not be possible for a person to go near enough to read it. And then this is a problem that you might see if you test it for yourself.
That makes sense. Thank you. There's a question from Gam.
Yeah, thanks. Thank you very much, Katharina, for the great presentation. I think you've done a great job despite the difficulties with the pandemic. I especially liked how you did your demo. So mounting the head-mount display on your chair, that was very clever. I have a question regarding, so I think during your talk, you've mentioned just donning a VR headset already kind of impairs your vision. And then you kind of mentioned kind of 0.5 of visual acuity. Is that based on some measurement that you took, or is it from a reference, or can you explain a bit more about how you came up with that?
Actually, we implemented an eyesight test with these Landl-Cs in VR. There are also these, I think you have these eyesight tests on some websites. You can do them where basically you have the test on your screen, and you have to insert your screen resolution and size and the distance from your head to your screen, and then it displays the Landl-Cs in the appropriate size, and you can do the test on your screen, right? So we basically implemented the same thing in VR. So we had a virtual distance of 6 meters, and the size that you'd usually use for these eyesight tests. And then we measured the visual acuity of the people. And this is how we found out that no one could reach a better visual acuity than 0.5 with this was, I think, with the HTC Vive Pro. For the HTC Vive, it was even worse. I think it was 0.4 decimal acuity. And this also means then if we want to simulate reduced visual acuity, we can, of course, only simulate something that's worse, even worse than that. because you already have just half your visual acuity.
That's great, thank you. Just a follow-up question. So you also did the follow-up study with AR using the front camera of the Vive Pro I. I can't remember exactly, but I believe the camera itself also adds kind of loss in resolution. Was that kind of considered in your studies, or are you considering that to be reflected in your studies as well?
That's an excellent point. That's why we did our measurements in VR, because as you have mentioned correctly, the front-facing cameras of the Vive Pro are really bad. They have low resolution and you have a noticeable lag as well. So this was more to demonstrate how this could work, but it's not something that I would use for user study, not with this hardware.
Thank you. Thank you for the great talk.
Makes sense. Any other question? Someone else? I wanted to ask about the landlord C sign.
Mhm.
When I did my eye tests, I was always using, or they presenting the E sign, which is, I don't know, it's a different
Mhm.
standard, I guess.
Yeah.
Was there a particular reason why the landlord C was used instead of something else? Or I'm not familiar of the advantages or difference.
There are different optotypes that you can use, and we basically just picked one of them. I think the landlord C is probably the most common one, but I think it's called Snellen E is also used quite often. So yeah, in theory, you could just swap the optotype and use something else. You just have to make sure that the size is correct, because for the tests, they usually define the size according to the smallest detail that you have to
Yeah.
identify. So for the landlord C, it's all about the size of the gap.
Yeah.
And for the Snellen E, you might have different sizes that you have to take into account.
I see.
But yeah, you could easily just use something else.
Yeah. And I like the approach you did for the visual impairment and trying to simulate it for other people for design. I was wondering if you came across or you know about other work that perhaps used for hearing impairments. So for example, like to simulate how you would hear things differently. And I know this is a completely different topic, but I was wondering if the same methodology will be applied for other medical simulation.
This is an interesting question. I mean, I know that there's different research in, as I said, yes, it's a different area, but I think there's also work on simulating audio and visual and also motion with such a motion suit to let you experience being old, essentially. But yeah, that's an interesting point to apply our approach to audio impairments. I didn't think of this yet. Thank you. That sounds
might
very
be
interesting.
A good idea for
future work.
Yes. Because here in the lab, well, I'm part of 2 labs here, but other lab, they try to use vibrotactile or vibration sort of to try to use it as an alternative way of communicating when you have hearing loss or hearing impairment. I was wondering if there is something maybe perhaps related to this, instead of adding assistive technology, as you mentioned, rather than simulating impairment. And then this way, we'll be able to design better rather than, let's give you something to improve.
Yeah, I don't know any particular work, but I'm sure there is some. I think there's quite some research in this area. Yes.
Um, last question, if no one is asking. Sorry. We here in the lab, we use EEG and hyperscanning and trying to understand more about the brain. Would you imagine there will be anything measured differently for visual impairment people when they are seeing things through VR? I don't know. What I'm trying to say, I guess, is it worth using EEG in this area, trying to understand more about the type of impairments that they may have? Would that give us anything, you think?
Hard to say. I mean, I think it depends on the simulation. If you'd have a simulation that would have an effect, or where you'd see an effect in the EEG of a normal sighted person, then I guess you could try the same with visual impairments, with simulated visual impairments, because then you might see in the EEG when person recognizes something very exciting later because they have this impairment.
Or they have the same struggle that we recorded before. I don't know.
Maybe.
It's a strange question, but I was just trying to think what could be the possibility here.
Yeah, it might be interesting to investigate this.
Oh, sorry. I would like to thank you again for your time and effort and presenting your work. It's been excellent to hear from you and observe your progress over the years. I can't wait to see where the future takes you and your future projects. And hopefully we'll meet again, either when you come to this side of the world or in another conference as well. Thank you so much.
Well, I thank you for the invitation. It was a pleasure to be here. I hope we meet in person next time.
Absolutely. Thank you.
Thank you very much. See
Thanks.
you.
Bye.
Bye.